Welcome to the video on artificial neural network part 4. So we are going to look at different activation functions used in neural network. So what is the use of activation function? Basically it determines if a node or neuron in a layer will be activated or not. What it means is whether that particular node or neuron will participate in the overall network or the model building process. The function adds non-linearity to the network, it helps in learning some non-linear features in the data. So without an activation function, the whole neural network is nothing but a linear equation, and therefore backpropagation cannot be done. So we'll try to understand this point. So let's say in our example which we saw in the previous videos. So this is the L1, right? So this is the basically equation for this node, right? For all these data points, and when they get multiplied with their respective coefficients and then get added, so this is what we get, linear equation. Then if when we have sigmoid function, which is activation function, which we used in the previous videos, then this thing gets fed to the sigmoid function and we get an activation value, the predictive probability value, which is p11. But if we get rid of that activation function, then this p11 gets reduced to this linear equation, nothing else. Now, if we go to the next layer, so in the next layer, the first node, if you look at the first node, these are the coefficients, right? This is what we saw in the video. So this is what the linear equation will be for the first node in the second hidden layer, and this gets fed into the sigmoid function in there. But what if we get rid of that sigmoid function? So let's look at this term of this equation. So this requires beta 11 and then p11. So now since we have gotten rid of the activation function, we are simply going to supply this L11 in the place of p11. So this gets multiplied to this whole equation. Finally, what we are getting is beta 11 theta 11 x1 plus beta 11 theta 2 x1 theta 21 x2, and so on and so forth. And if you look at this term beta and theta, if you multiply, what you're getting is scalar value. So this term gets reduced to a linear equation. Only thing is, instead of theta and beta, we have got theta into beta for each term. If you do the same, expand this, you will get the same linear equation. And if you add all of them together, you'll get nothing but this same equation where this theta will be changed to different value. That's all. So it doesn't work like a neural network. It becomes like a simple linear regression. That's why activation function is needed. So there are types of activation functions which we use in neural network. The one we have already seen is sigmoid function, then tanh, then ReLu, rectified linear units, then Leaky ReLu, another version of ReLu, and then softmax. So we'll see what are they. So sigmoid function, as we have already seen, sigmoid function is defined as 1 upon 1 plus exponential of minus x, right? So if we assign 0 to x, for what we get is zero point 0.5, right? So for the value of x 0, we get the sigmoid function will give us 0.5. If x is 10, then the sigmoid function gives us 1. If x is minus 10, then sigmoid function gives us 0. So for large value of x, we are getting 0. For negative x, we are getting 0. For large positive value of x, we are getting 1. And for x as 0, we are getting 0.5. So I've just taken one example here, like x varying from minus 10 to 10 and incremented by 0.01. And then we have calculated the value of y, which is the sigmoid function. And this is the gradient of sigmoid function, right? We have already seen it. It's sigmoid into 1 minus sigmoid. That's all it is. So then we plot both, right? We calculated y, we calculated sigmoid function, sigmoid value, and the gradient values, with respect to x, and we plot it. What we get is this plot, right? So this is the sigmoid. You see it is varying from 0 to 1. And what you see is for the values in the negative range, for the first few values, it is flat. So there is hardly any change in sigmoid, is hardly any change in y. Then suddenly when we reach here, it jumps, it goes for even for slight change in x, it goes up very high, and again it reaches a plateau here again, see. So again it becomes, so derivative here is 0, derivative here is 0. That's what you're saying. When you plot the derivative, which is this, you get 0 here, and you get 0 for this also, you're getting 0 here, right? This is what you see in the plot. Now it converts any value. The sigmoid function converts any value, any number between 0 and 1, and it does not have any negative values. It is centered at 0.5. You see this 0.5, not 0, somewhere here, right? This is what we saw, right? So so somewhere here. Then gradient, the maximum value of gradient of sigmoid is 0.25, you see, and it flattens out quickly on the left side and right side both. Therefore, this gradient is not very good for this sigmoid function, is not a very good activation function for a large network where we have lot of hidden layers. It doesn't perform well in backpropagation. What happens is, since the value of gradient is very small, and as we move from in the backpropagation, as we move from output layer to hidden layer, and as we go on up to input layer, by the time, if it is a very large network, by the time we reach somewhere in between, the value keeps, the gradient keeps getting reduced because it keeps getting multiplied, right? We saw in the video that error terms, we calculate error terms using gradient of sigmoid function, and since the value is so small, it keeps getting reduced, and at one point in time the gradient becomes 0, it vanishes. So it basically kills the gradient, this sigmoid. So this creates a vanishing gradient problem, and network either does not learn, or it learns very slowly. So this is the problem with sigmoid function. So the better option is tan h function, which is defined as exponential of x minus exponential of minus x upon exponential of x plus exponential of minus x. So for 0, what we get is 0 actually. So if we supply x as 0, this tan function will give us 0. For x as 10, we are this tan function gives us 1, and for the value minus 10, we are getting minus 1. So you see the value varies from minus 1 to 1 and centered at 0. That's what we're going to see. So I've taken the same example like sigmoid function, and this is the gradient of tan h. It is 1 minus fx square. So 1 minus tan hx square. This is the gradient function. So we'll plot it and see how it works. So see, it looks like sigmoid, but it goes from minus 1 to 1. Again, it is quite flat in the beginning, then suddenly it rises for a small increment in x, and then again it becomes flat. You see, so even this derivative, it becomes 0 wherever it is flat, and the value of this goes up to almost like 1, you can see here, right? So it is better than sigmoid function for sure, and the values vary from minus 1 to 1, right? It's centered at 0. The gradient is maximum 1, so it's definitely better than sigmoid, where the maximum is 0.25. So it's stronger than sigmoid. The optimization is easier in tan h than sigmoid. So these are the advantages over sigmoid. However, the issue of vanishing gradient doesn't get resolved. So then we come to ReLu function. So ReLu function is defined as fx is equal to max 0x. So maximum of these two. So whichever is higher, it will give us that value. So for x as 0, we get 0 value for ReLu. Any positive value of x, any value of x which is positive greater than 0, this function will return the same value. If the value of x is negative, then this function will return 0. So this is what it varies, either 0 or the x, takes either of these two values. So again, looking at the same example which we saw on the previous slide. So here derivative is defined as derivative is 1 for all the values of x greater than equal to 0. For all the values less than 0, it is 0 actually. This is how it is defined. So let's plot and see what happens. So this is the ReLu function. This is plotted, and this is the derivative. You see it is 0 for all the values less than 0, the derivative, and it suddenly becomes 1 for any value greater than equal to 0, right? So this is what we are getting here. So it converts any value between into a number between 0 and x, right? So basically takes 0 or x, basically that's what it does. Either it takes 0 or it takes x, depending on the value of x. And then gradient, the maximum gradient is again 1 here, right? This is what we see here, right? If any, for any value of x less than 0, it is 0. If greater than or equal to 0, it is 1, right? So this is what we are getting here. Then it resolves the issue of vanishing gradient, and it is computationally less expensive compared to sigmoid and tanh. So this is another good advantage of ReLu, using ReLu. So, but it has a problem. It results in some of the neurons becoming dead. So if it starts like training at the beginning, some weights or some nodes or neurons are weak, like some weights are weak. So it kills that neuron. It doesn't activate that neuron basically. So that neuron doesn't participate ever again. So that is called dying ReLu. So to resolve the dying ReLu problem, they came up with this leaky ReLu function. So leaky ReLu function is defined as fx is equal to max 0.01 x. Now what we do is we take a very small fraction of x. Instead of 0, we are taking a small fraction of x. And this is the example I have taken, 0.01. You can take a smaller value than this. And then I've just taken the same example like before. And this is the gradient of this ReLu function, which is 1 for all the values of x greater than or equal to 0. For all the values of x less than 0, it is 0.01. So let's plot and see what happens. So you see, this is the leaky ReLu. See, it's actually not 0. Below the, when the value of x is less than 0, it is not becoming 0. It is taking a fraction of this x. So it is gone little down. There is a small slope here. It's not a straight line close to 0. You can see that. And if you see this gradient, so gradient has taken again, 0.01. 0.01 instead of 0, right? For any value less than 0, it has taken 0.01, right? Less than, for x less than 0, and for x greater than or equal to 0, it is suddenly has become 1, right? This is what it is. So it basically converts the value into either 0.01x or x, any of these two values. That's what it does. So maximum gradient is 1 here, as we have seen. Then it performs really well on large, just like ReLu function. It performs very well on large network. It also resolves the issue of vanishing gradient, just like ReLu function, and it tries to solve the dying ReLu problem. And that can be quite debatable. That depends on domain and the experience. Thank you so much for your patience and watching this video. If you like, share, and subscribe.